solar photovoltaics, or PV, is no longer just an alternative energy source. It is rapidly becoming the backbone of the global energy transition.
It really is. And it has launched us into a truly massive new phase, the multi-terawatt era. We already have about 2 terawatts of PV in service globally.
And that's just the beginning.
Exactly. If you look at credible projections for decarbonizing the planet, many scenarios suggest we need upwards of 75 terawatts installed worldwide by 2050.
75 terawatts, that figure is just staggering. Okay, let's unpack this. This kind of monumental growth requires more than just, scaling up existing factories.
Right.
It demands a completely new approach to what our source material calls learning.
It's a great framing. For this deep dive, we are pulling the key insights from the comprehensive analysis titled Historical and Future Learning for the New Era of Multi-Terawatt Photovoltaics.
And when this study talks about learning, it's not just lab coats and R&D, is it?
Not at all. It defines it really broadly. It's the combination of formal R&D, yes, but also the cumulative experience you get from massive manufacturing cycles, the global expansion of knowledge, and active international collaboration.
So our mission here is really twofold. First, we look at the incredible historical learning that got us here, that propelled PV to become the cheapest electricity source in history.
And then
Then we pivot to examine the radical new focuses, things like reliability and critical resource management, that have to emerge for us to hit those 2050 targets without, frankly, overwhelming the planet's resources.
Because if you need 75 terawatts by 2050, that means we need to install and manufacture on average 3 terawatts of capacity every single year until then. The learning curve has to speed up drastically.
It's a fascinating historical curve to look at. The sheer global growth of PV has been nothing short of remarkable. The study notes that PV has actually outpaced every other major energy technology in both manufacturing capacity expansion and in the rate of price reduction.
And this success is visually striking when you look at the data this study presents. It's just exponential cumulative deployment, massive cost reduction.
We're talking drops of over 99% in module price since the 70s.
Exactly. Plus significant efficiency increases and, importantly, steadily increasing reliability.
So how do we explain that dramatic improvement? I mean, analytically, it can't just be good luck.
No, and that is precisely where the experience curve comes in. What's so fascinating here is that this is an empirical mathematical concept. It captures how proficiency improves as a function of cumulative output.
So like every time you double the total number of solar panels ever produced globally.
So the cost of the next unit drops by a predictable percentage, yes.
It's like learning to build cars, right? The 100th car you build is cheaper than the first, but the 100 million is exponentially cheaper because you learned so much.
Precisely. It's holistic learning. And this learning was actively accelerated. It wasn't passive. We saw shared knowledge through training, collaboration, cross-licensing of intellectual property across the globe.
And standardization must have been huge.
Massive wins from standardization, like the regularization of wafer and module size, which just streamlined the entire supply chain.
And crucially, government R&D played an outsized role in de-risking the technology, particularly around reliability. Was there like a single program that really changed the industry overnight?
The study points directly to the U.S. government's Jet Propulsion Laboratories Block V Reliability Improvement Program from decades ago. That program was critical because it directly shaped the testing sequence we still use today.
And that sequence is the globally recognized stress test for panels, right? For listeners who don't know the acronyms, it's the IEC 61215 qualification testing.
Correct. It's the standardized set of accelerated stress tests, temperature cycling, humidity, damp heat, that allows utilities and banks to trust that a panel, no matter who made it, will last long enough to guarantee a return on investment.
So that directed R&D laid the foundation for cost reductions by boosting confidence.
Exactly. It's a separate, valuable form of learning.
Okay, so building on that historical success, we have to look forward. Price, performance, and reliability, they all have to keep advancing.
Even though, as the industry matures, those incremental cost decreases get smaller for every extra bit of deployment. The low-hanging fruit is gone.
The problem is physics, isn't it?
In a way, yes.
And here's where it gets really interesting. Today's state-of-the-art silicon modules are rapidly approaching their theoretical limit. We've hit about 26% efficiency, And this study suggests the peak for a single-layer silicon cell is likely around 27%.
Right. So to drive down the cost per watt substantially further, we need a breakthrough that goes beyond silicon's fundamental capacity.
And that breakthrough is?
It's centered on what are called tandem architectures, specifically the combination of perovskite materials layered on top of traditional silica. This is the major R&D focus now because it offers a path past that hard 27% limit.
But if these are so much more efficient, why aren't they everywhere already? What are the practical advantages and, I guess, the risks?
Well, the potential is quantified, and it's significant. By stacking two junctions, one optimized for different parts of the solar spectrum, you get a huge boost. Small area perovskite silicon cells have already hit an astonishing 34.85% efficiency, and commercial size modules are already at 30.6%. This study predicts that reaching over 35% efficiency in the coming decades is very realistic with continued investment.
That immediately helps the economics of the whole installation.
Precisely. Higher efficiencies mean you need less physical land area or roof space for the same power output. That directly reduces what we call the balance of systems costs.
Can you define BOSS's costs for us quickly?
Absolutely. BODIS is everything other than the module itself. The inverters, the racking, the wiring, the construction labor, and critically, the land.
So if your module is more efficient, you shrink your land requirement and all those associated costs.
Dramatically. And on top of that, all thin film tandems offer the theoretical potential for even lower raw material consumption and a reduced carbon intensity in manufacturing.
But there's a critical challenge, right? They aren't ready for that massive 3 terawatt per year scale yet.
And this raises the essential question about future learning. Can they scale fast enough? This study notes that tandem technologies still require substantial improvements in reliability and scalability before mass deployment.
So they have to get up that experience curve, and fast.
Fast enough to contribute meaningfully, and they have to prove they are as stable and long-lasting as silicon.
Which brings us to reliability. You know, if I'm a utility company preparing to invest billions in a project that needs to run for 30 years, the most important cost isn't the module price, it's the certainty that it will last.
Of course.
So why is module longevity so critical in this multi-terawatt era?
Because reliability translates directly into manufacturing demand. If we can increase the average module lifespan from, say, 25 years to 35 years, we instantly reduce the required manufacturing capacity needed to maintain that 75 terawatt base by a full 40%.
Fewer replacements.
Fewer replacements mean less manufacturing stress on the system and fewer resource constraints.
So new technologies must match or exceed that established silicon reliability to be adopted. What's the process for getting there?
What's fascinating is that the pathway for new tech to gain adoption isn't arbitrary. It follows 4 necessary steps to become market viable. First, you need a clear, consistent specification of module performance.
That's table stakes.
Second, you must reach a predictable short-term energy output, proving it works today. Third is identifying early failure potential using those standardized accelerated stress tests we talked about.
The IEC standard.
Right. And fourth, and this is the hard one, the mitigation of risks from new or unknown performance degradation modes.
That fourth step sounds like a constant game of catch-up. Every time the design changes, new risks pop up.
It is. The product constantly evolves. Thinner glass, larger wafers, new sealants, and that evolution inevitably introduces new risks. This requires dedicated and specific research to mitigate.
And that can't be done in a silo.
No, if we connect this to the bigger picture, this kind of rigorous reliability learning requires collaboration across the entire community. You need to develop new standards, establish centralized facilities for long-term testing, and strategically use smaller, controlled beachhead markets for initial deployment.
Okay, now let's shift focus to the new learning required for the future. We're moving from a singular focus on cost reduction to a dual focus on sustainability.
A huge shift.
The new mission is minimizing adverse societal and environmental impacts, which, according to this study, won't emerge from cumulative experience alone. This needs directed R&D.
The primary benefit, of course, is massive CO2 displacement. As PV installations grow towards 75 terawatts, the carbon offset will be enormous. That's the most significant environmental metric.
And beyond that, we're seeing improvement in manufacturing efficiency itself. Key metrics like energy and water consumption per module have decreased over time.
Often driven by manufacturers increasing wafer and module sizes and just boosting throughput. But the real material focus is on material thrift, getting more power out of less stuff.
Right.
We've seen silicon consumption per watt come down 8-fold in the past 2 decades.
How did they manage that reduction in silicon?
Primarily through thinner wafers and reducing kerf loss. Kerf loss is essentially the sawdust, the material wasted when you slice the silicon ingot into thin wafers. Learning how to slice more efficiently saves huge amounts of material.
But the biggest looming constraint isn't silicon. It's
It's silver.
silver that's used for the conductive grid lines on the surface of the cell.
Correct. And while usage per watt has decreased substantially, the projected sheer scale of future silicon module production will unfortunately lead to an overall increase in silver consumption.
Potentially bumping up against global availability and price constraints.
That's the concern. So R&D is urgently needed to address this before it bottlenecks the 75 terawatt goal.
What are they looking at?
Current R&D is focused on replacement or significant reduction, exploring methods like copper plating or advanced screen printing techniques that use a fraction of the silver. But here's the critical paradox the study highlights. Sometimes material thrift creates new problems.
Tell me more about that trade-off.
Well, the study points out that the industry's push toward material thrift, like the move to larger modules coupled with increasingly thinner glass cover sheets, some as low as half a millimeter, has actually led to an increase in mechanical failure rates in the field.
So we make the panel more sustainable by using less material, but we make it less reliable by making it more fragile. It's a zero-sum game unless we innovate past that trade-off.
Exactly. That demonstrates the necessity of specific reliability research tailored to these evolving designs. We can't just assume the old standards hold up when we change the underlying materials.
Which leads directly to the third route to enhanced sustainability, the circular economy. We need to design for ultimate reliability, easier reuse, and most critically, effective recycling.
And while current volumes of decommissioned modules aren't huge yet, now is the time for R&D on module design for disassembly and recycling technologies. The goal here is horizontal recycling. Meaning recovering high-value materials like silicon, metals, and glass in a form pure enough to go back into making new PV modules. We want to avoid downcycling them into low-grade aggregate.
What are the main challenges to achieving that horizontal recycling?
Preventing impurities from contaminating the recovered material is huge, and managing the increasing complexity of materials as PV technologies diversify. When you introduce those new tandem layers, recycling gets much more complicated.
The study actually synthesizes the R&D agenda from the 4th Terawatt workshop on this, right? It lays out some clear priorities.
It does. For cost, the focus is researching next-generation thin-film PV and replacing scarce materials like silver.
Okay.
For reliability, the long-term goal is incredibly ambitious, reducing the average degradation rate of modules to less than 0.1% per year.
Wow. Think about that longevity. That's essentially guaranteeing the panel will last 50 years.
Precisely. For design for sustainability, the priority is focusing on design for disassembly, maximizing recycling yields, and establishing large-scale, cost-effective markets for those circular materials.
And last one.
And finally, design for adoption, enabling a future of PV everywhere by designing panels for dual use and seamless system integration into buildings, vehicles, even agriculture.
So what does this all mean? The core takeaway is that the PV industry has to shift its mindset. Historically, the focus has been on explosive growth and aggressive cost reduction. To maintain the necessary momentum towards 75 terawatts, the new focus must become resilience, resources, and sustainability.
And that shift is non-negotiable. Global learning, shared experience, and continued R&D investment are essential, especially for activities like preemptive recycling design that have massive future global benefit, but lack immediate financial incentives for industry to undertake alone.
Securing this abundant, affordable, and resilient source of energy for humanity is the goal.
It is, but the monumental challenge isn't just scaling production, it's deciding which resources, whether that's reliability lifespan, material thrift, or installation area, we are most willing to compromise on to get to that 75 terawatt goal. The investment, manufacturing, and adoption decisions made today about circularity and resource management will pay globally transformative dividends tomorrow in terms of economic growth and reduced pollution and poverty.
A compelling final perspective on the delicate balance required for the future. That was our deep dive into the insights extracted from the study, historical and future learning for the new era of multi-terawatt photovoltaics.